My dear students, you will have an inclined plane problem on the exam. An inclined plane is this thing here, the little wedge with a box on it. So I want to be really clear. One of a problem like this is on your exam. I'm going to change it though. I will change some things. So normally I write down my ideas in orange. What I want to do though is I want to write down things that you could put on an index card and transfer them safely to your exam and be fine. So if your inclined plane is facing this way, let's just first begin with a free body diagram. So I'm going to draw a dotted line that represents the plane, and I'm going to move it over here. And then I'm going to adapt everything based on that. So again, let me just draw a normal force vector perpendicular. Yeah, so this goes here. All right. So this goes here, and I will draw a arrow there. So that's my normal force. That's the normal reaction force. Now, the gravity force, the weight, goes straight down. I want to be clear. This reaction force is perpendicular to the inclined plane. Now, there may or may not be one, but I'm going to draw it. Let's actually draw a friction force here going up the plane. The assumption is the box wants to slide down. And lastly, the gravity force we're going to split into two components. I'm going to write those in a different color. Okay, so we're going to have the gravity component times the cosine of theta, and we have this other component, Fg times the sine of theta. This only works for inclined planes, this splitting up of the trig values, meaning this. There are other problems where you split up into trig values, sines and cosines, but this idea that the sine goes this way only works for inclined planes. And the way to remember this is sine makes you slide. Okay? Now, we just did part 1. Now it says, show that the coefficient of friction between the block and the plane is 0.6. Let's set up our equations. So it says the block is just about to slip. Let me switch back to orange. Just about to slip means equilibrium. That means the forces balance at first. So now I need to set up equations. Also, let's be clear. In this, our x and y components go this way. This is the y, and this is the x. Let's actually balance our forces. So this is another thing you want to get memorized, okay? If you are in equilibrium or not, let's write down the most general equations that we can, okay? So for this inclined plane, you're going to end up getting that r minus fg cos theta equals 0. I'm going to let you write that on an index card for this exam. You need to be able to draw this free body diagram and come up with this on your own with no help at all whatsoever, like in like 20 seconds. That sounds really cruel, but that's how the IB is going to work. If you can't, then you have to simply just commit this to memory. Then we're going to have Fg sine theta minus the friction equals, now I'm going to write the most general rule here, m times a, and in equilibrium, a equals 0 in equilibrium, because we're not accelerating. So here, let's go ahead. Oh, and then there's a final formula. Okay, neither of these are in the data booklet. Not in booklet. These are a consequence of Newton's second law. Here's the formula that is in the data booklet. The friction force equals mu times the normal force, where mu is this coefficient of friction here. I'm writing that in purple because this is the data booklet thing. So let's go ahead and let's get the coefficient of friction. So R minus Fg cos theta equals 0. So I'm going to actually get R equal to Fg cosine of theta, where Fg is the weight, m times g. Now we also have Fg sine theta minus, that should be a friction force there, minus the force of friction equals, and in this case we're in equilibrium, so it equals 0. So in other words, I just want to emphasize we're in equilibrium. So that's going to give me the friction force equals Fg sine of theta. Now I'm going to do a little bit more of a general solution. I'm not going to put in numbers just yet. Let's do the following. So I'm going to use the fact that, and sorry, I put Fn here. I need to write that as R for the reaction force. So I have that the friction force is mu times the reaction force. Let's actually plug in these values that we have here. So I'm going to say Fg sine theta minus mu times, equals mu times Fg cosine of theta. And when I isolate mu, mu actually equals the tangent of theta. Memorize this. It's not in the data booklet, but it's really useful. And when I put in 30 degrees here, you want your calculator in degrees. Mu ends up being, it actually ends up being 0.57, but we're going to round that to 0.60. All right, now let's do part B. So mu, we're still going to treat mu as though it's 0.6. And now we're going to say that theta is 60. So here we go. Now I'm going to use the formula here, Fg sine theta minus the force of friction equals m times a. So here we go. So mg sine of 60 minus 0.6 times mg cosine of theta equals m times a. I cancel the m's everywhere. So I'm going to end up getting g sine of 60 minus 0.6 times g cosine of 60 equals a. So when I isolate a, I will end up getting 5.7 meters per second squared. So that is it for the inclined plane problem.